Hi, realizations with decoders is the topic of this mini lecture. As you remember, I hope you have watched the mini lecture which discussed the decoder, I mean binary to one of n decoders. And as I said, the decoder, this kind of decoder can be viewed as a min-term generator. So I have just introduced this one. It is the most common one, but there are also 3 other versions of this decoder having inverted outputs, having inverted inputs, or having the both inverted inputs as well as inverted outputs. Let's start with this one, and let's recall that it can be viewed, and it is actually the min-term generator. So if you put the variables, let's call them A, B, C, you would get on the appropriate corresponding outputs the min-terms of the same indexes as output indexes. So M7 is available here, M6 is available here, and so on, M0 here. So you can use then OR gate, as you remember, it is a sum of products, canonical form, and you can implement the function in canonical form using the selected min-terms and add them logically using a single gate. So you got the target function. Okay, so any function can be obtained in this way. Having all the min-terms, you select only the ones where the function is equal to 1 in the truth tables and add them together to get y outputs function. What about this variant of the decoder? In this case, what the inverters on the output do is, if you have a, let's say, min-term 7, let's go ahead, min-term 7. If you don't have inverter here, you will get min-term 7, which is A times B times C. But if you invert this, you simply invert this. And using De Morgan's law, you get A inverted plus B inverted plus C inverted. And what it is a max term M. What about the index of the max term? It corresponds to 0, 0, 0. The same, it corresponds to 1, 1, 1, because the inversion are put in the opposite rule, using the opposite rule. So the variable is 1, it is put with dash. So 1, 1, 1 is 7. So it is max term of the same index, and this is a rule for the remaining ones. So instead of min-term generator, you have max term generator. So let's denote the output functions as being max terms of all the max terms of the 3 variables A, B, C. So in order to get any function you need, instead of using OR gate, you must use AND, because max terms must be multiplied. It is a product of sums. Each max term is a sum, and this is a product gate. You get y in this way. What about the third case? The third case means that the interpretation of these bits are inverted. So first you must invert A, B, C, and then process this signal in the same way as in the case of the most common version of the decoder. So For example, if you put here A, B, C 1, 0, 0, it is internally interpreted as 0, 1, 1. Nice. So 1, 0, 0, A, B, C is then inverted into 0, 1, 1, which means 3 in decimal. And that's why by putting 1, 0, you'll get M3 instead of M4. So this is where 1 would occur, okay, in this situation. So from the point of view of your function, you put simply 4, row number 4. So you expect to have M4, but M4 will be available on M3. So here you've got M4, because you must interpret the numbers in a negative manner. So 0, 1, 1 is either 1, 0, 0, yes. 3 is 0, 1, 1, but you must invert the bits. So you get M4. If you have 1, 0, 0, if you invert, you've got M3. If you invert bits in, you've got M2. So the order of the minterms are the opposite. Look, yes? Here you get 6 is 1, 1, 0, so you get 0, 0, 1. So 0, 0, 1 is minterm 1, and it is a minterm 0. So the inversion of the bits gives you minterm generator, but in the opposite order, in the descending order. Yeah? Exchange. You must change the order. So let's do it. So I wipe out this, and you get a minterm generator, but you must be aware that the order is opposite. M0 here and M7 here. And you can combine these two using two rules, this one and this one. So you, instead of minterms, you've got maxterm in the opposite direction. Please, I'll put labels. They were missing. Okay, 4, 3, 2, 1. So you get maxterm 0 here, maxterm 1, and so on, maxterm 0. Maxterm 7. So similarly, you can use here OR gate, because you've got minterms must be ORed. And in the last case, if you have max terms, you use also AND gate to get Y. Okay, let's do an example using these 4 kinds, these 4 variants of decoder. And as you can see, it is divisibility by 2 or 3 detector. It is not right now. I must fill in the values. So it is the 0 is divisible, 1 is not, 2 is, it is, 5 not, 6 it is, and 7 not. So I can write down the y of x2, because x2, x1, x0 is a number, input number, as a sum of minterms. And minterms as 0, 2, 3, 4, 0, 2, 3, 4, and 6. But also as product of max terms. It is a less number of max terms here as 1. And what is missing is 5 and 7. Okay, you've got these 2. So in the first case, let's return to the minterm generators 0, 2, 3, 4, 6. 0, 2, 3, 4, 6. So your task is to deliver these 0 as well. 2, 3, 4, and 6. And that's it. It is a decoder of divisibility by 6 by 2 and or 3. Then, if you have max terms, you need 157, max term 1 to be multiplied, max term y, max term 5, and max term 7. And you do the same in this situation. You need max term 7, max term 0, which is here on the upper side, and also max term min term 2. Min term 2 is available on output 5. You need also min term 3. Min term 3 is on output 4. You need min term 4, which is on output 3, and you need min term 6, which is here on output 1. And you get the same solution of the detector. And the last one is to deliver max term 7, max term 5, which is here, and max term 1, which is here. And that's it. You've got the same function using 4 variants of the decoder. But looking at the solution, you would prefer this version. Yes, you have less cost. The cost factor of this gate is only 3.1. Of this gate 3.1, and here you've got a 5.1. So I would prefer this. But if you don't have max term versions, I mean the inverted output versions of this, and you have to use this or this, how to lower the cost? How to lower the cost? There is an approach to have the same cost as in this case, and even lower. I will show you in a moment. So instead of writing y, you are finding not y, or sorry, it is also a change in the names of the signals. These are not ABC, X2, X1, X2 must be connected to input 2, X1 to input 1, X0 to input 0. And of course, you must repeat this for all the cases. All right, so let's return. Instead of writing down or implementing y, you implement not y of x2, x1, x0 equals sigma, and the remaining only 3 min terms, 1, 5, 7, 1, 5, 7. Okay, so let's change it. So instead of implementing y, you implement not y. Not y is min term 1 added with min term 5 and added with min term 7. You've got the same cost factor as to, but the function is not y. Well, you should transfer it or change it to be y, simply by replacing or with nor. Okay, and now you've got y, the same function as before, but the cost got lower. Okay, got lower, and is even lower than this. As you remember, how many transistors are there in the AND gate? 2-input AND gate has 6, and 2-input or NOR has 4. So it is a generic, yes, less expensive version, and the cost factor academic one is the same, 3.1. And for practicing purposes, I propose you to change this. Okay, change this and use NOR instead of OR. Of course, in the case when you have more min-max terms here, you can change this gate also into NAND. Okay, implementing not y and then inverted. Okay, so in any case, if you've got more ones than zeros, you can implement it in another way, having less number of inputs of the gates. So be aware of it. Yes, and minimization is the main goal, the most important.